Okay, so last week we went to the Fab Lab, um, and so I thought I'd just try to give, we saw a lot of stuff and heard a lot of details. I thought I would just give like a real quick 5 minute type summary of the equipment that's available in there, because so with the idea of moving on to some kind of like robotics project, um, it's nice to just sort of have in your head like, oh, we need to make this arm that does this thing. Maybe we could make that uh, out of a thin board that we can cut with the laser cutter, or make this joint out of a 3D printer, that kind of thing. So so the Fab Lab equipment. So first, there's just sort of like, I'm just going to call it the tools. There's some stuff that would be like in a wood shop, that's not really particularly engineering focused, but can be useful sometimes. Um, so there are a couple of band saws. There's a drill press. There's a miter box for cutting angles. That's also just like a saw that you can cut ends at different angles. Okay, that's not really what the Fab Lab's about, but that stuff is there. And then second is the, sort of engineering equipment. Engineering fabrication equipment. So that's really the heart and soul of the Fab Lab. And first, there's a vinyl cutter that lets you do very detailed, clean, cut out shapes and letters and stuff out of vinyl tape. I don't know. It's nice for making signs and things, nice for making labels on things. There might be better uses, but for me, that one's not a real big one. The laser cutter could be very useful to us, I think. So the laser cutter cuts thin pieces of wood. What other materials did he say? It really does not cut metal at all. So no metal with the laser cutter, but mostly sort of thinnish strips. Of wood, some kinds of plastic. And it can do very intricate computer design shapes with very fine details. So if you want to cut something very precisely, that's something to think about, as long as it can't be a big 3D shape. It's basically just a thin surface. Then there's the CNC router. Come back. CNC router. And that can do more built up three-dimensional shapes. It removes material, so you can start with a big block of wood or something and cut out things until you get this shape. But that means that you can't have any enclosed surfaces. You can't use a router to cut up a hollow ball. You know what I mean? It works best on wood. It can do some thin aluminum. Acrylic. And then last, and really the one that, it's what I've used the most, so it's what I know the best, and maybe that's why, to me, it seems like it would be the most useful to us. But the 3D printers just let you, make any shape, three-dimensional thing with enclosed, it can be hollow on the inside or whatever. The only material that it uses is ABS plastic, but ABS plastic, I think for most applications of ours is going to be strong enough, and it's pretty stiff and stuff. So that's kind of my summary of what's available in the Fab Lab. Please, feel free to email me or whatever if you have any questions about what stuff does, and I either will know it or will be able to find out. So maybe as we start talking about the rest of robotics, or as we start thinking about what kind of projects we'd want to do, think about what kind of things would go into it, and just start to think like, okay, yeah, you need a case for this. How would we build a case? Are we going to build it out of wood? Are we going to screw it together? Are we going to try to build a contoured plastic thing? I should say also that some of the materials in the Fab Lab are sort of expensive, but the Fab Lab has a lot of material, and I think within reason, we really don't have to worry too much about limiting the amount of material that we use. I think there would be a point where Martin would start to wonder like where this is all going, but there's quite a bit of stuff in there. Anybody have any questions or comments about the Fab Lab tour from last week? Okay. So there's been pretty good interest in working on some kind of project, or nothing says there has to be one. We can have parallel things going with things that different people are interested in, but the suggestions I've seen so far have been all related to robotics. And so that's what I want to talk about today, just sort of a very bird's eye view of how the different things that you need to do in a robotics project fit together. There's programming, there's microcontrollers, microprocessors, there's electronics, and how do you get all these things to talk together? That's kind of the what I want to talk about today. And before I can talk about anything else, I first just need to talk about two sort of components of electricity that you need to have something in your head about. So first thing I need to bring up is electric current and voltage. Okay. You do a lot of stuff with current and voltage in physics too, but in daily life, I think people tend to think of these two as sort of interchangeable. But they both are they're very specific aspects of electricity. And so the way I want to introduce this is if you think of electricity moving through a wire as water flowing through a pipe. So to get water to flow through a pipe, you need to apply a pressure difference. You need to have a higher pressure at one place in the pipe than the other place. That difference in pressure is going to make the water move along the pipe. Okay, you with me on that? So we're going to think of voltage as the equivalent to a pressure difference in the pipe. And we're going to think of current as basically how fast the water is flowing through the pipe. Maybe think of it as like water flow or water mass or water volume per second. So water flow per second. The current is what powers the device, any kind of electronic device. Voltage, though, that equivalent to the pressure that makes the electricity move along the wire, is the, I'll call it the impetus, you know. I don't mean that in like a science way, I just mean it as like the thing that makes the current flow is the voltage. You apply a voltage at 2 points in a wire and it makes electrons try to get from one side to the other. So voltage is the impetus for the current. Okay, so let me just give a quick example. So say this is a liquid and there's a straw and here's you drinking this milkshake or whatever. Delicious. I'd recognize you anywhere. Looks just like you. Okay, so how does that happen? So say that straw is the pipe, you know. How do you get the liquid to move from the cup to the mouth? Well, the pressure at the surface of the water, basically, since a glass isn't very big, essentially the pressure through all of the water in the glass is 1 atmosphere of pressure. Okay. And I don't know an actual number for this, but when you suck on a straw, what you're doing is causing a lower pressure in your mouth. So let's just call it 0.9 atmospheres. I don't know if that's close or not close or what, but you create a lower pressure in your mouth. And so if you think about the straw now, you have 0.9 atmospheres of pressure up here, 1 atmosphere of pressure here, and you could represent this. So notice those are 2 different points. You have pressures at each of those 2 points, right? But one way to think of that would be, well, there's a pressure difference between those points where the higher pressure is on this side, the lower pressure is on this side, and the pressure difference is 0.1 atmospheres pressure difference, right? And what matters to get the water to move is not whether this is 1 atmosphere and 0.9 atmospheres or 1,000,000 atmospheres and 999,000. What matters is the pressure difference, not the individual pressures. And so this pressure difference makes the fluid move like that. Okay. So now with electricity, so say this is a wire now. How do you get electricity to move from the point on the left to the point on the right? Just like every point in the pipe has a pressure, every point on this wire has an electric potential. Okay, and you don't, that term isn't something that you tend to hear that much, but say that this has a 5-volt electric potential. And this point has a 2-volt electric potential. Then what that means is, each point by itself has an electric potential, but the voltage is the difference in electric potential, and that can only be between 2 points. Okay, so there's a difference in potential, in electric potential of 3 volts with the positive, the higher on the left and the lower on the right. And this electric potential difference is called the voltage. Okay. And just like water always flows from the higher pressure to the lower pressure, current always flows from the higher electric potential to the lower in the direction of decreasing voltage. Okay, so if you want to get electricity into a hopping rabbit toy or whatever from a battery, any kind of electric device, you need to cause a potential difference between one side of the wire that goes into the toy, into the electronic device, a lower electric potential at the other side. That's a potential difference between the two parts of the circuit, and that makes electricity flow into it. Okay. Anybody have any questions about this yet? It's such a simple analogy, but it really, for people who, especially when you're new to thinking about electricity, it's a really helpful way to think about it. And when you get confused, a lot of times going back to this analogy and thinking about it this way can clear up a lot of things. Okay. Anybody here heard that analogy before in high school physics or something? Yeah, right. It's used quite a bit because it's really helpful. Okay, so now that we have that, I'm going to talk about robotics as a combination of two different parts. Okay. Where is this? Okay, so robotics is made up of sort of two pieces. The first one is you have to have some kind of processor that uses a computer program to read voltages between pairs of pins. I'm going to call these input-output pins, I/O pins. And generate voltages between other pins. Okay, so you load a computer program onto this processor, this chip. And let me show you a picture of that. So this is probably the company that makes the processors that would be the best choice for us. These are all Raspberry Pi models. They have a few different types. They're this one I know. I think I read that 6 centimeters. So they're pretty little. You know, that's a very blown up picture. And when I say that, so you can see the microprocessor is in here. That's battery. That's memory. But underneath that is the chip. You know. So you see the chip. You see some stuff to, you know, some ports for charging the batteries and loading memory and whatever. And then here, these are the pins that I'm talking about. These are the I/O pins. They call them GPIO, so that's general purpose input output. And so you can have your program reading, say, if you have this pin hooked up to some electronic device like a optical sensor or a sound sensor or something, you can compare the voltage of that pin with the ground. And if that optical sensor sees something, it applies a voltage there. And when your program sees that there's a voltage between that pin and the ground, then the program goes into some loop that does some command. It then applies a voltage over here with the ground. And you use that voltage to power an arm to move, to roll wheels. That's the idea. Okay, so that would be the end of it, except, let's see. So the difficulty is that the voltage that these microprocessors can produce at these input-output pins are small, and 3 volts or 5 volts. So the voltage that you can read or assign at the microprocessor pin is small, 3 or 5 volts. But what's the real problem? I mean, with 3 volts or 5 volts, if you have the ability to produce a lot of current at 3 or 5 volts, you can get a lot done, actually. But the real problem is that these microprocessors can't deal with, the currents they can deal with are tiny. The current they can read or produce is tiny. So for the Raspberry Pi, that's something like 30 millivolts. Okay, so if you had the right, if you were able to generate enough current with 5 volts, like for example, if a wall outlet is 110 volts, but say that your wall outlets instead were 5 volts, you could still get a lot of useful electricity out of the wall, but you can't power very much with 30 millivolts. Okay, maybe some LEDs. You can get certain kinds of stepper motors that can move very small objects with 30 millivolts. Okay, so what do you do if you're trying to build a robot where you're trying to use these pins to decide whether to roll wheels, move an arm, do real physical tasks? How do you use those pins to do these tasks? That's where the circuit analysis comes in. And so what you do is you use the pins to open switches that can handle bigger currents. Those switches, the two types that we're going to need to use are transistors. Transistors can do two things. They can be switches that just allow current to flow or not to flow, or they can be amplifiers. For us, we're just going to need them as switches. The other type of electric switches that allow big flows of electricity are relays. Anybody have any questions about just sort of the basic idea of a microprocessor? So there are various ways that you can get your programs onto these processors, depending on the kind of processor you have. With Raspberry Pi, you can buy Raspberry Pi versions that allow you to load an operating system and do the programming on the thing. Or they also have one that's cheaper and smaller where it can't load an operating system, but you do the programming on a computer, then load it onto the chip. And then those commands are on the chip, and then you have this little chip that just has those commands stored, and it knows if it reads 3 volts between here and here, it creates a voltage between here and here, Okay, so here's the idea of transistors and relays. As switches. So if this is the transistor or the relay, and when you wire it, it doesn't look exactly this way. You have to learn, the different kinds of transistors, different kinds of relays. You wire them differently, but the idea is the same. You have the input. The small input voltage there. And if you have a certain threshold of voltage between these two, it opens the circuit or closes. I guess you can do it either way, but it affects whether electricity can flow through bits 1 and 2 or whether it's stopped. Okay, so like you can think of it as like if the microprocessor is connected to, this is connected to one pin and this is connected to one pin. Okay, if your program says apply 3 volts between this pin and this pin in the ground or whatever, Then when there is 3 volts there, that allows current to flow through here. And so, let me write this down. So if the voltage between the input and the ground is 0, no electricity can flow between 1 and 2. If the voltage between input and ground is non-zero, so say now it switches to 3 volts, then electricity can flow freely from 1 to 2. Okay. So a very simple sort of illustration of what it would look like is if this is your Raspberry Pi or Arduino or any other kind of microcontroller, and these are the general purpose input output pins. So I'll call this pin 1, and I'll call this, well, I'll call it G for ground, but it could be pin 2, whatever. So you take a wire and connect these to the relay or the transistor. And then over here, you have one of these 2 things connected to a battery. Okay. And the other one connected to the thing that you want to power. Let's say it's connected to a motor. Okay, so how does this work? So if your program decides for whatever reason, because of inputs it's gotten or because a certain amount of time has gone by or whatever, that's all decided in the program you write. If your program sends a voltage of 3 volts between these 2 pins, okay, then that allows the battery to power the motor. If your program sets the voltage between these 2 to 0, then that closes this switch, I guess opens the circuit, and this battery stops powering that motor. So now your program, even though the processor can't run this big motor, it takes too much current, too much voltage, you have a way for your processor that can only produce a small amount of current to tell this motor when to turn on and off. Okay, so that's how those 2 things work together. Any questions about that? I think it's a really cool process. It's really fun to the first time I did it was in a class that I was teaching here actually, where we did some sort of basic robotics. And I just thought it was so much fun. Like, you program this little thing, you have this little thing here, you wire it up, put all the blah, blah, blah. And then you have this big thing that's like, I mean, the amount of force you can generate or the amount of power that you can, it's unlimited, you know, it's only limited by the strength of your battery, you know, but you can get your program to lift these big things, you know, throw balls, do all this stuff that there's not nearly enough power in the processor for. Okay, so then the last part of this is dealing with the devices themselves. So this part has to do with programming and not much else, just programming. Okay. And then you have to deal with transistors and whatever, the switches. That's kind of its own thing. Then setting up these circuits, that's just sort of like circuit design, like you would take in circuits 1, or you would do a lot of that stuff in physics 2. So the circuits to power the devices. So devices, so each device, whether it's a light or a motor or a sensor, has an operating range of voltages. And if you exceed that range, you're going to do damage to the device. So you have to be able to get voltages to this device within a certain range. If a specified voltage is applied, the device draws a known amount of current. And electronics, you can always online find data sheets for them, and this information is all given in the data sheets. So in order to get the desired voltage to a device, you have to use resistors. And the idea of a resistor is, resistors act according to, who knows the law for resistors? Yeah. I think this has been like total review for everybody. Maybe it's okay to have review sometimes, but Ohm's law. And what Ohm's law says is, if that's a wire and there's your resistor, okay, and there is some voltage going over the resistor, so the electric potential on one side of the resistor is higher than on the other side by this amount V. There's a current going this way, so current always goes from the high electric potential to the low electric potential. and I'll call that I. And if the resistance in this resistor is R, then Ohm's law says that the voltage is equal to IR. Okay, so if you have a higher value of resistance for, let's say, a given amount of current that's going through it, then given amount of current, and you increase the resistance, you're going to increase the difference in electric potential between the two sides. Okay, so I can't really go into math with this, but I do want to show, like, I want to show an example of how this kind of thing would work. Okay, so let's say that you have a power source that's a 6-volt battery. And you want to use it to power a device that needs 3 volts and draws 0.02 amps of power when you apply that voltage of 3. So how would you do this? You'd have to set up a circuit that has resistors in it so that wherever the device is in the circuit, the voltage is 3 and the current is 0.02. And I'm just going to draw a circuit that works so you can see the basic idea. We can talk in the future about how you would do this. But so if you have your battery over here that has a voltage of 6, okay, you can't just go straight from the battery to the device because the voltage would be 6, right? So that's going to destroy the device. But if you do this, let's see. If you put a resistor here that's 136 ohms, and you put a resistor here that is 1500 ohms, and then you put your device like this, if you do the mathematical circuit analysis, you see that this is the voltage between the two sides of this device is exactly 3, and the current is exactly 0.02 amps. Okay, so like I said, we can talk about how you come up with that stuff. It has to do with a couple of other laws and whatever, and it's not super complicated. It's just too complicated to fit everything into 50 minutes. But so yeah, if getting into like robotics projects, we're going to be learning how to program the microcontroller. We're going to be learning how to use the transistors and relays as switches, and we're going to have to do a little bit of circuit analysis to use the devices. Anyone have any questions about that? Anyone get any small useful things out of that? Okay, good. All right, that's all I want. My expectations are low. Okay, well, I guess over email and stuff, we can start to think about what kind of microcontroller is going to work for us. Like, I really think Raspberry Pi is the way to go, but like I said, there are a few different models, so we have to choose. They're so cheap. the lower price models are under $10. I mean, we could get a box of them, you know. And we're going to have to think about what kind of projects we want to do. I've always liked the idea of building a rolling robot that just rolls around Normandale bothering people as they try to get to class, but I don't know. Yeah, I think so too. Okay, so yeah, something like that would require hooking up optical sensors, maybe echolocation kind of sensors, and we'd have to have wheels and figure out what it's going to look like and figure out what kind of motions it's going to do, and then just start little by little assigning these different tasks to different people, and start with small tasks, and then, you know, just depending on how much time we have, just keep building out from there, you know, until we take over in Normandale. Okay, well, great, thanks for coming. So next week, Dr. Hattie Dambrowski from the biology department is going to come talk about her career, how she ended up in what she does, what kind of research she does. I think it'll be really interesting, sort of a nice non-engineering talk. Yeah, hopefully you guys will have questions for her and stuff. So think about if there's anything you'd like to, anything you've ever wanted to know from a biology professor, but were afraid to ask. That's next week. Okay, see you then. Talk to you over email soon. See you next week.
Is there like, do we have like an online thing with just cover information?
Oh, send me an email and I'll get you that information.
Cool.
All right. Yeah, sure. You too.